Recording in progress.
Good morning, everyone. Let's start. Okay, last 2 weeks we were looking at oscillator circuits, right? So we considered 3 oscillators, Greenwich oscillator and relaxation oscillator, and the last one is ring oscillator. Okay, today we might consider current source. Probably today's lecture and the next half lecture will go on to this 3 to 4 hours. So basically, principle voltage control current source, circuit design, simulation, and application. Okay, so here there's no lab in designing current source, but in section 3 there's one lab. However, even though there's no lab, I strongly suggest I give you a homework, which is a design. Okay, so which is not which will not be conducted like a lab, but on your own time, more free time, you go to the lab, preserve the lab, look at the analog lab schedule. I think your batch rep can reserve when the lab is free, reserve the lab and go there. Only few of you, about 20 students. So maximum 7 groups, 1 session is submission. So find a free session, reserve it, go there, and try to get some experience on this, right? It is a homework, but the homework is a kind of lab, okay? But it is not counted to the final marks. It is for your own experience, okay? Remember, education is very expensive outside Sri Lanka. So here you have all the facilities, and also you have some limited time this semester as well as another 2 semesters, right? So 14 weeks into 2 plus the remaining weeks, which is almost 10 week or 11 week, then you would have less than 30 or 40, less than 50 weeks altogether, right? So make use of the resources. If you graduate, then you will find really difficult to get all these equipments. Wisely use your free time. Okay. So again, there's a homework you need to do by yourself. Section 2, current source, principles, voltage control, current source, circuit design, simulation, and applications. You also can do some simulations on this. You can use LT Spice, right? Now, what you are going to simulate? Remember, this is a design module, analog circuit design, right? Therefore, you have to approach in the design point of view. In reality, identify few parameters which can change. For example, temperature, power supply variation, right? What are the other parameters? It will change. List it out. Try to change 1 or 2 parameters and see the effect. That's what you should do. Okay, try to change, for example, supply voltage variation. You can easily mimic that condition in the lab, right? When you change the supply voltage gradually, but you should be able to measure it, measure the variation. Therefore, you had to come up with certain arrangement. I think you know how to do that now by this time, right? What you can do is you can connect your circuit to a small series resistor like 1 ohm, measure the voltage drop across the 1 ohm, then you can measure the current, right? Then you can measure the voltage after the resistance, which in other words, but exact supply voltage to your circuit, and then you can set the supply voltage there in the supply so that the desired supply voltage at this point, that means after the resistor, right? So before the resistor connection only you are going to give the supply voltage, but after small resistance resistance, you can measure the voltage and change the supply voltage accordingly to get the desired supply voltage here. Generally, not our lab supply voltages. I'm not sure whether that facilities are equipped there. Depending on the supply voltage equipment, there are sense pins. That means if one supply and the sense pin also connected to the same point where we wanted to where we want to give the supply. So what happens in the sense pin, the supply voltage will keep increasing until the sense pin's voltage is to the desired voltage or the voltage that we set. So that arrangement is there normally in the testers. Okay, so why is that? If you want, you have the facility to separate the supply and sense. So the point where you sense it, that is the place the actual voltage, the set voltage will appear. That feature is there in supply voltage, power supplies, in certain power supplies, okay, depending on the time. Mostly testers use that kind of approach. Right, let's move on. So today we are going to talk about current source. Right, simple current source. We are going to disqualify one by one, or we are going to identify the potential difficulties by using simple circuits. So this is a simple current source. What we do here is we use an op-amp, right? So there's a resistor connected to the non-inverting terminal, and then there's a load to the output. So since V plus is connected to, it has to be negative feedback, therefore V plus is connected to ground, therefore V minus also almost ground. Therefore, the current through the RS is Vs over RS. Current through the RS is Vs IS, in other words, IS is Vs over RS. That IS completely flow through the RL because the current through the inverting terminal I minus is ignored. That means it should be the way, right? So you have to select the amplitude in such a way, right? IL is equal to I load current is equal to IS and Vs over RS, which is equal to Vs over RS. So RS is constant, therefore you can, by changing the Vs, you can change the IS. But this is the simplest way, right? You have already learned this. But what is the negative aspects of this? That is, your output voltage has to be below zero. Because V plus is zero, V minus is zero, I into RL, therefore voltage drop is on the upper side, right? The high voltage to the high voltage side of the RL is zero, therefore low voltage is negative voltage. But this is, then you have to do some other arrangements to shift the ground and all these things. That is troublesome. Okay, and also not only that, supply voltage variation to the op-amp will affect the output. Right? Supply voltage variation to the op-amp will have some influence in the V out. So that also brings some uncertainty. Because this section is current source. So what is the meaning of the current source? We have to provide the current that the user specify. Right? If user wants 1 amp, you have to give 1 amp. User wants 50 milliamp, you have to give 50 milliamp. Right? So it has to be constant. But here also we have constant current, but that current value is sensitive to the supply voltage variation of the op-amp. Then what happens if the RS has some tolerance? That also will come to the picture. So VS is plus or minus 10%, RS is plus or minus 10%. Then we have maximum minimum variation here, right? So this model or this circuitry is not welcome because of three important reasons. One, output voltage has to be below zero, which we don't want most of the time. Second, sensitive to variations in Vs, right? Third, resistor tolerance. But circuit is very simple. Again, if you look at RL, the power consumption is the RL is acceptable because it's a load. But power consumption in the RS is not acceptable, right? But anyway, if there's a source, there's a series resistance. But if you leave that one apart, there's no other resistance. But power consumption in the op amp, that is also significant. Therefore, the efficiency of this circuit matters. How much power it consumes and how much power it gives to the load. Right.
Recording stopped. Recording in progress.
Okay, sorry, got disconnected. Okay, let's start. So one of the application of this current source is for the capacitive touch screen. Um, you can see a simple circuit. You might have come across some applications in PLL, right? We need current source frequently to design our circuits. This is one of another application which is very common. And what we have here is a current pulse. Okay, current pulse. So what happens if we have current pulse? You know that if we send constant current, the capacitor voltage will increase, and then when it goes to negative, it will decrease, right? So you can see the current waveform in the red, and the capacitance waveform voltage equals the capacitance in blue, right? So the capacitor will charge, discharge. That cycle keep going. We have current in the positive direction as well as in the negative direction. It will switch. Therefore, the capacitor will reach a maximum voltage, right? What will happen there? There's a touch which is parallel to this capacitance. So the capacitance will increase because of the hand external capacitance which is introduced by our finger, as well as the internal capacitors. Therefore, charging timing constant will increase. So what will happen? The peak voltage will reduce. Okay, if we go to the next slide, you can see the peak voltage. Say this is the threshold we get. The peak voltage will reduce because additional capacitance. Time constant is RC increases, capacitor increases, RC increases. Therefore, peak voltage reduces. So if we take the midpoint as the threshold reference, now what happens? The capacitance, the peak voltage will not cross this reference because of the external capacitance, right? So that is the detection. I mean, if you look at this, we have a reference voltage here, and then there's an op-amp. This is a comparator. The capacitance voltage is compared against this threshold voltage. If there's a touch, this voltage is below the threshold voltage, sorry, is below the reference voltage. If there's not external touch, this voltage is above reference voltage. Therefore, we can get some output here, right? So that way we can detect the touch. Right. Another application is the charge pump PLL. Remember in the PLL phase lock loop, you might have heard this one, right? The charge pump. So what happens here, we need to measure the phase difference between two clocks, two digital clocks. So we give one phase here and the locally generated phase here, so that we have to have the reference phase matched to locally generated phase, right? So, but how do we realize it? We have to measure the phase difference. When QA and QB is equal to 1, this is an AND gate output is 1, so it issues the reset. Therefore, QA, QB is going to 0 value, right? But if either one turn on, there's no reset value, because in order to have the reset value, both has to be 1. So what's going to happen? Suppose if I get the positive edge here first in the external, so the QA going to be 1, whereas QB going to be 0. So since QA is 1, it connects the switch, right? You forget about the logic functionality, but reality is when this is activated as 1, it is close to the switch. Therefore, the capacitor CP is get charged. Suppose if this one QB is first, then this one close, capacitor get discharged, right? So if QA is leading, we have positive CP or positive voltage across the capacitor. If QB is leading, we have negative voltage across the capacitor. So that capacitor voltage drives the VCO, voltage control oscillator. Uh, so it will be the input voltage. We continuous voltage here because this is easy to have a stable voltage across the capacitor. Now noise effect is much less because capacitor CP will charge, discharge and produce a constant produce a stable voltage at the input of the VCO, less noise at the output. So in other words, the clock jitter is much less in this case. And the VCO output is the local clock. Reference clock is here. It can be reference mean it can be from another system or whatever, so that the incoming clock is phase match with the local clock. So voltage control oscillator here. This is the PLL, phase lock loop. Right. So here we had to have matching gate delay. What is the impact of there are two flops and also there's one AND gate. So the charging discharging connects here, but creates some voltage here. However, there is some uncertainties due to this gate delay, right? So what will happen? Gate delay, that means the reset issued by the AND gate, but there's some delay. What will happen if QA and QB is 1 and not reset? That means during that processing time, right, gate delay time, QA QB will not be equal to 1. Even though both, I'm sorry, QA QB is equal to 1, but reset is not going to be there during the propagation delay of this gate. But so if QA and QB is going to be 1, that means both switches are closed. Right? Both switches are closed. That means this current goes all the way down here. Provided that I1 is equal to I2. That should be the case. I1 is equal to I2. Therefore, here we have a need of matching current source. Right? Matching current source. That means same current source should go through this. When both switches are closed, this becomes the midpoint. That therefore, this current goes through this, but the potential here, then there are going to be some imbalance. Okay. So there is some effect, but we ignore that effect here. Well, in the capacitor, since the current is constant, IC is equal to C into dVC over dt. So since the current is constant, IC is constant. So dVC over Vt is a linear curve. Vc is equal to linear. That is why we have linear curve here. It is not a charging discharging curve. It's a linear curve. Charging and discharging is happening linearly. Why? Current is constant. dVc over dt, governing equation is dVc over dt is equal to constant. Therefore, Vc is linear. Okay? The total line is linear here. Here also solid line is linear. Analyze the effect of I1 minus I2. What will happen if both these current sources are not matching? slight difference is there. Then that difference is going to affect the charges which I stored in CP. Right? Either CP is going to get charged to come to that point, or is going to discharge. If there's a mismatch, the balance has to go through this path. Again, there's an assumption that input impedance of the VCO is very high. The current to the VCO is negligible. So whatever the remaining current goes through the CP. CP is the bigger capacitance we need, or we had to calculate the capacitance accordingly. Right. So we saw two applications here which are important. Current source 1. In this case, what happens to, we use two potential divider. Current is through the MOSFET, but we control the gate voltage of M2 by using a simple potential divider, right? So the current through M2 under this condition is governed by this equation. I will derive this equation later, no worries. Once we meet physically, I will derive this because I need to use the whiteboard. It's a bit difficult to explain this through this. So the current through the transistor is given by ID2 is equal to W over L mu COX gate voltage VGS. VGS of M2 is equal to VDD divided by R1 plus R2 multiplied by R2. This is a VGS. VGS minus VTH square plus lambda times VDS2. Drain source voltage. Okay. Drain source voltage. This is the equation. In fact, this is channel length modulation effect 1 plus lambda BDS2. You can ignore that. If you ignore it, this becomes beta times VGS minus VT into whole thing square. Right? It's a constant. It's a constant. Once you set this constant, then the current is constant. If we don't have this one, but what it introduces, okay, there's a linear variation in the ID2 if we increase the drain source voltage. So if you look at the characteristic waveform, it will be like this, exaggerated, slope exaggerated. Okay, most of the time it will be flat. It should be flat. Right. If you look at this is a constant, right? This part is a constant. Again, W/L ratio, that W/L of the transistor, right? This part is just VGS, voltage, gate, source. Okay, minus VT holding scale. This part is the variation part, drain source voltage, because that is what more important. What we expect is I out has to be constant. Okay, I out has to be constant. We need a constant current source. So we try to keep VGS constant by having potential divider. But however, variation VDD is going to affect here. So if VDD is plus or minus 10%, this is linearly going to affect, but sorry, quadratically, because this is square, right? Lambda is constant always. So question is, when we change the load within our limits, how much variation the current source will have? That measures the quality of the current source. Say voltage, right? If we set 5 voltage with different load setting, how much variation we will get it? If it is negligible, good quality power source, power supply, right? Otherwise, the quality has to be improved. So we have to get better quality power supply. Same here, to the load variation, to get load variation, how much current variation will appear. But that variation depends also depends on the VDD variation here. Resistance variation. I think last time, I'm not sure in the first session or not, we have worked out the, I'm not sure this, we haven't met yet in person, right? Yeah. Okay, we will see. Variation here will have some effect, right? Then what are the other variations? Transistor PVT variations. What is that PVT variations? Let's discuss that in a while. Okay. A simple current source circuit uses a MOS transistor bias with a voltage divider. This circuit is sensitive to power supply voltage and the threshold voltage VTH. Threshold voltage may vary by 50 to 100 millivolt from wafer to wafer. Both mu and VTH exhibit temperature dependence. A good analog design should be insensitive to process, supply voltage and temperature variations. It should be insensitive. But we have to do something to design. This is not the finalized current source. We are trying to see some simple current source and identify what are the sources, what are the quality compromise because of what. So in this case, power supply variation, PVT variations of transistors play the role. I will discuss this when I see you, probably next week, when I see you in person. So basically, this is the equation we used. ID is equal to beta times BGS minus VT into VDS minus VDS squared by 2. This is the equation, but what happens here? VDS is equal to VGS. Okay, I don't know whether you remember we have that characteristic to discuss now. Okay. Right. I will give you a detailed explanation in the next session. I skip this slide for the time being. PVT variations. Let's look at PVT variations. Process voltage temperature. Okay. When we fabricate circuits in wafer, it has to go through many processes, right? But each process has its own deviations, right? For example, temperature. If you set it to 100 degrees Celsius or 500 degrees Celsius, it will not be exactly 500 throughout the process time. It may have some plus minus variations, like our clock, right? If we set it to 100 megahertz, it will not be 100 megahertz all the time. It has some plus or minus 1% or 10% variation, like our resistor typical value. So every process will change, and therefore there is a variation, process variation. Because of that, temperature changes, chemical density changes, light intensity changes. Due to those changes, we may have some deviations in the transistor characteristics also. If you take resistor also will have some deviations. That is why you are getting some tolerance, plus or minus 10% tolerance when you buy the resistor. Even though it's empty components, you will go through at least plus or minus 1%, right? If you buy expensive one. So there's a variation. Non-uniform condition during diffusions of impurities. This is depositing LB mods. Non-uniform condition. That's what I mentioned. Light intensity, chemical density variations, right? All included here. Variation in dimensions of the device. Yes. Suppose you want to make a opening with 1 into 1 micron size. Will it be exactly 1 into 1 micron? There can be plus or minus. Some variations in the dimension. WOL variations in the most transistors. Same here. Length. Right? With variations in the width, variations in the length, can be some plus or minus. So considering all this process variation, the effect is some characteristic change. So what is the maximum current, what is the minimum current, what is the maximum delay, what is the minimum delay, considering all these variations. That is called process variation. Supply voltage variation. Our supply voltage to the device may vary. If it is handheld device, 3.3 volt to 3 volt, or whatever the power rating it is, may vary with the time usage, right? Sometimes it's because of the noise, it may vary. However, whatever it is, higher the supply voltage, electrons move faster. Lower the supply voltage, electrons move slower. Therefore, signal delay also less when we have high supply voltage, and signal delay is small. Sorry, less means is a small value. Signal delay is more or higher value when supply voltage is small, or small in the sense in the minimum. Right. Next, operating temperature variations. What happens? Temperature increases. When temperature increases, electron starts to vibrate, but not vibrate, but you can assume that it gets more energy and starts to move from its own place, and therefore the directional electrons which carry the current will find with difficulty when moving in a straight line, when electrons move arbitrarily from its own position, right? Therefore, it's something like if everybody stands up and walk in a crowded hall, you find difficulty to cross that hall, right? Because there are so many people walking here and there. So your time to cross the hall is longer compared to if everyone sit in the hall in its their place and compared to the time that you cross in that condition. Therefore, same here. Electrons, most directional electrons which carry the current will find it difficulty to, or it find uh, more delay crossing that conductor. So comparing all these, temperature variation throughout the chip due to power dissipation in the most transistors. So why temperature variation first of all occurs? Because with the time the chip dissipates power, right? Therefore temperature change happening within the chip. Electron and hole mobility depends on the temperature. Electrons and hole move slower when temperature increases. Propagation delay increases with increased temperature. Right. So because of these PVT variations, the signal delay also experience. So because of those changes in the signal delay, what kind of impact this current source may have? This transistor may go through that PVT variations. And therefore, in other words, the characteristic curve also may shift up and down. Right. Therefore, the point is we are not considering the delay too much here, but the shift in characteristic curve. For example, when you set VGS is equal to 2 volt, what is the current? Say the current is 2 milliamp, but if you have different PVT 0.8, depending on the PVT condition set here, in simple terms. So the variation in current because of the PVT condition, longer the time we use, high temperature, because of the high temperature, the characteristic curve might shift and it may introduce some currents. We may expect some current shift here. Okay. Good analog design should be insensitive to process supply voltage and temperature variations. So now what we are trying to see is even though we have simple circuit here, it is not fit because of two reasons. That means not fit means if you have application which can tolerate high variations in the current source, then that is fine. But in this circuit, PVT variations of M2 and resistor variations, supply voltage variation may affect the performance. So, right, may affect the performance. That's what you should take away from this topic. Right, another current source. Now we have I reference. We slowly moving forward to a complicated current source which can have better quality. Why we go for, we make our circuit a little bit more and more complex? Because we want to have better quality current source. Right. In this case, we have I reference. We want a current source, but we are using a current source here. But it is okay. Why? Current source here is the low quality one. Current source here is a high quality one. Okay, we are talking about the quality. Right. So that means the low quality one means the effect of this will not carry forward to this side. So what happens here? There's a current source. and you see there's a connection here. So in the words, VDS is equal to VGS, right? And therefore, this enters into saturation region, right? But by having the right current here, even though we have variations, this transistor will have PVT variations, this transistor will have PVT variations. The point is, if we choose matching transistor, M1, M2 matching transistor, that means W over L is 2 is equal to W over L1. It means if you look at this equation, if two transistors having, maybe I use, yeah, this equation, W over L ratio is matched. This is constant. Therefore, this part is equal to this part of both transistors are equal. That's what the point here is. Right? But variation here will not affect much. What is carry forward from here to here is VGS is equal to VDS. In order to put it in an approximate place, we use this current source. Right? And therefore, VGS, because these two are matching transistor, so whatever the current here, almost we will have the same current here with better quality. That's what the point here is. Matching transistor, right? So, but this current also, source also have some difficulty. You can see, to have the matching transistor, we had to meet WL2 is equal to WL1, right? But the ratio has to be matched. Now, what is the I out over dV out? That means this is the I out, dV out is 1 over R out 2, because the okay, slope dI out over dV out is the slope, right? But in fact, 1 over R out 2 is the slope, because I is in the y-axis, therefore 1 over R out 2. Let's look at the output impedance of this circuit. If you go only, we have another one. Right. If you consider this one, right, the small signal model of this transistor, in the output side between I out and the ground, we have a current source which is GM2 into VGS2 and R out 2. But how do we measure the output impedance? We connect the input impedance to ground and keep a small supply voltage here and measure the current. So when we connect the input side to ground, this input side VGS goes to 0, and therefore, but we can say output impedance is R out 2, right? Is R out 2. That's why our output impedance is 1 over G out 2. Oh, that's also okay. The reason is, okay, now I have to draw the equivalent circuit. Okay, consider this one. If we short the input, because we want to measure the impedance, we short the input. VGS2 is 0, right? VGS2 is 0, and therefore R out 2 is remaining in1, this will disappear, right? R out 2. But in the normal time, ID2 is split it into GM2, GS2, and R out 2, right? Into two part here. Or else we can have it's a current source, please note that. Therefore, we can in the open circuit, if you don't have no load condition, right? GM2 RO2 is VGS2, right? GM2 RO2, sorry, GM2 into VGS2 is equal to RO2 into, no, I'm sorry. Yes, output voltage is GM2 VGS2 into RO2. Okay, the open circuit condition. Okay, let's continue. Multiple current source. Multiple current source. That means you may want to have different current source from the simple reference. All we have to do is we have to have a different ratio, W over L ratio, W over L ratio. But this is giving the reference. Therefore, by carefully changing the W over L ratio, we can have multiple current source. Sometimes some circuits need different current source. Okay, here, cascade design. It means, if you look at earlier, output impedance is where it is here. It becomes R out 2, right? Which is very similar. Now, if you want to have a higher output resistance, cascade design provides that large output resistance, right? So R out Vx, normally what we do, if we have, if we want to measure the output resistance, we short the input, right? We short the input and apply a small voltage and measure the current. Voltage divided by the current gives the R out. That's the case, right? So when we have BGS3, when we short it, right? So GM into VGS3 is here. The source point is going to be at the different voltage, right? So R out 4 plus GM into VGS3, but VGS3 is negative here. IX minus GM into VGS3, because VGS3 is negative here. Into R out 3, current through the R out 3 is IX minus this current into R out 3, right, is that is the potential across this Vx. We are trying to replace the Vx, but it's Vx. R out 4 into R out 4 into Ix. Total current completely flows through this, because Ix here, only here is it divided into two branches, but comes here. R out 4 into Ix, that's what we have here. And potential across this is R out 3 into current through R out 3, which is Ix minus Gm into VGS 3. Okay. And then we find the Vx divided by Ix. So what Bp, this potential is VGS 3 minus VGS 3, right? Which is Ix into R out 4, this potential. Therefore, R out becomes, we can simply substitute R out 4 plus 1 plus GM3 R out 4 into R out 3. So comparing R out 4 plus R out 3, R out 4 into R out 3 into GM3, this product is much higher because R out 4 into R out 3, this is R out 4 plus R out 3. Say for example 1K, 1K, this becomes 2K. This is 1K into 1K, this becomes 1M 10 to the power 6. Therefore, GM3 into R out 4, R out 3 is the output resistance. We increase the order. Okay, we increase the order. Generally, this, if we choose this gradient is much less, right? Longer channel, short channel effect is there. So we can get a higher output resistance here. More immune to systemic error in the fabrication process than the cascade design. Here, what exactly we do, two matching transistor in this case. This side decides the output load current and also it decides the output impedance, cascade design. This side we have shorted, we make sure that VDS is equal to VGS. Here also the same case. There's an I reference here. But these are open, right? So what we do here, in this case, we change, because anyway these two are matching transistor, right? One decides the VGS equal to VDS, other one is open. Therefore, if we bring that condition here, it is more immune to systemic errors. Because this one is decided by shorting drain to gate. However, without leaving these two open, here we short. So this setup shows better or more immune to errors. Especially in temperature variations, right? Power supply variations. Because this path also restricted, this path also restricted. Please note, since VGS is this transistor is shorted, that means gate is shorted to source or drain. This NMOS. Then what happens? The current here is fixed. Similarly, in this path also current here is fixed. But we can fix this current, and this current is by opening here and here is more immune to errors. But here what we do, this short will fix this current, this short will fix this current, but ratio of these two WOL decides the current flow compared to I reference. Okay. So the variation in I reference, even though we have low quality one here, is absorbed is absorbed through these two transistors. That means variation in VDS. Remember, VDS is equal to VGS here. Variation in VDS. Similarly, here variation in VDS, this part is changed to force this side to have a right current. Variation in VDS here, because here variations is better, I out, right? So it will force the current on this part. Better variation means less noise. Small is not high, I mean more variation, that is more problem. So W over L ratio, but W over L ratio will not have variations, right? There are two things here. You have to be careful. One, variations in the manufacturing. W over L may have slight variations, but it will not change with the time. Okay, it will not change with the time. Some variations like supply voltage, temperature, that will change with the time. Okay. Right. Anyway, I will discuss all these points in the next session as well, because looking at different aspects, and if I miss anything, I will discuss. This is your homework. Design a current source using the current mirror and characterize your circuit performance. Measure the output range of your current source. Analyze the effect of supply radiation. Demonstrate your circuit to your instructor, but here if you want to discuss with your instructors, you can do so. Obviously, this is the report is not required, but let's take some soft approach here. Not demo, demo and get feedback. Sorry, demo your circuit and get feedback from one instructor, okay, or from master instructor. It's better because this instructor has to be assigned for the analog circuit module. No need to submit. Okay. Right. Because batch to batch, I will change slightly the assignments, homeworks, right? Also the lecture notes. That is why I do not give lecture notes at the very beginning. Once I finish the module, depending on the questions they ask, I also include some additional points to make them go through easier. So Once I finish one session, I will upload the lecture notes. Okay. And right. That's all I want to cover today. Probably because I'm taking, I know that I'm not covering 2 hours. This is just to move on because most of the circuit design aspects has to be discussed in the class, physical class. Okay, so I will keep some of the items to discuss. Anyway, I will come back to these points at some other time. Um, okay, let's conclude today's session with this.
Recording stopped.